Today we're diving into one of the most fascinating phenomena in condensed matter physics: how mechanical deformation of graphene can create pseudomagnetic fields that mimic the effects of real magnetic fields reaching hundreds of Tesla. Let's start with the basics. Graphene is a single atomic layer of carbon atoms arranged in a perfect hexagonal lattice. It's one atom thick, yet incredibly strong, and has extraordinary electronic properties. Here we see the honeycomb lattice structure of graphene. Each vertex represents a carbon atom, and the bonds form perfect hexagons. This structure is the key to graphene's remarkable properties. Graphene's electronic structure is unique. Near the Fermi level, electrons behave as massless Dirac fermions, with a linear energy-momentum relationship. This is described by the famous Dirac cone. The energy equals plus or minus h bar times the Fermi velocity times the magnitude of the wave vector k. The Fermi velocity is approximately 1 million meters per second, which is 1/300th the speed of light. This remarkable velocity means electrons in graphene move extremely fast, giving rise to relativistic-like behavior in a condensed matter system. Now, why do we care about magnetic fields in graphene? Real magnetic fields quantize the electronic states into discrete Landau levels. This is quantum Hall physics. The Landau-level energies are given by plus or minus the Fermi velocity times the square root of 2 times the elementary charge times h bar times the magnetic field B times the level index n. Let me ask you a question. How strong are typical laboratory magnetic fields? The strongest continuous magnetic fields we can create are about 45 Tesla. Pulsed fields can reach perhaps 100 Tesla, but only for microseconds. So laboratory fields range from about 10 to 100 Tesla. These are already enormous fields, requiring massive infrastructure and enormous amounts of energy. Now here's where it gets fascinating. Through mechanical strain alone, without any real magnetic field, we can create what we call pseudomagnetic fields that can reach values of 300 Tesla or even higher. How is this even possible? The answer lies in the way strain modifies the electronic structure of graphene. Strain changes the hopping parameters between carbon atoms, and this change can be mathematically mapped onto an effective vector potential. When you deform graphene, you're not changing the magnetic field. Instead, you're changing the geometry of the lattice it's. But mathematically, this geometric change acts exactly like a gauge field on the electrons. The pseudomagnetic vector potential is proportional to h bar over E times A times T, where A is the lattice constant and T is the hopping parameter, times the strain tensor components uxx minus uyy and negative 2uxy. The key insight is that it's not uniform strain that creates the pseudomagnetic field, but rather the gradient of strain. You need inhomogeneous deformation. The pseudomagnetic field equals the curl of the pseudovector potential, just like in electromagnetism. This is why we need spatial variation in the strain. One of the most effective ways to create strong pseudomagnetic fields is through triaxial strain. Imagine pulling graphene in 3 directions at 120 degrees apart. Here we see triaxial strain configuration. 3 forces pull outward at 120-degree intervals. This creates a very specific strain pattern that maximizes the pseudomagnetic field. Let me walk you through a back-of-the-envelope calculation to show you how strain translates into pseudomagnetic field strength. The carbon-carbon bond length in graphene is 0.142 nanometers. The nearest neighbor hopping parameter is approximately 2.8 electron volts. Let's say we apply a 10% strain. This is quite large but achievable in carefully prepared samples. Now here's the question. What pseudomagnetic field does this 10% strain produce? The pseudomagnetic field scales as h bar times beta over E times a squared times the strain, where beta is a numerical factor of order unity related to the strain configuration. Plugging in numbers, h bar is 10 to the negative 34 joule seconds times 10 for beta and strain, divided by 1.6 times 10 to the negative 19 coulombs times 10 to the negative 20 meters squared. This gives us approximately 60 Tesla. That's comparable to the strongest continuous magnetic fields we can create in laboratories. With optimized strain configurations and larger strain values, researchers have achieved pseudomagnetic fields exceeding 300 Tesla. This is far beyond what any real magnet can produce. You might ask, is this just theory, or has this been observed? The answer is that pseudomagnetic fields have been directly observed using scanning, tunneling microscopy, and spectroscopy. In 2010, researchers at Berkeley used scanning tunneling spectroscopy to directly observe Landau levels in strained graphene nanobubbles. These nanobubbles naturally create the right strain pattern. A graphene nanobubble forms when graphene adheres to a substrate with some trapped material underneath. This creates a dome-like structure with highly inhomogeneous strain, perfect for generating pseudomagnetic fields. Now you might be thinking, wait, if we're creating magnetic field effects without actual magnetic fields, doesn't this violate fundamental physics? Doesn't this break time reversal symmetry? Excellent question. The answer is no, because pseudomagnetic fields do not break time reversal symmetry. Real magnetic fields break time reversal symmetry, but pseudomagnetic fields do not. Here's the key. In graphene, there are two inequivalent valleys in momentum space called K and K prime. Electrons at the K valley see a pseudomagnetic field pointing up, while electrons at K prime see it pointing down. Mathematically, the pseudomagnetic field at the K valley equals minus the pseudomagnetic field at the K prime valley. This valley-dependent sign ensures time reversal symmetry is maintained. This also means you won't see a Hall effect from pseudomagnetic fields. The Hall currents from the two valleys exactly cancel. This is how you can distinguish pseudo from real magnetic fields experimentally. Let's dig deeper into the physical mechanism. Why does strain act like a magnetic field on electrons? The hopping amplitude between sites I and J depends exponentially on the change in bond length delta Ij. Here beta is about 3, and A is the equilibrium bond length. When you stretch a bond, the hopping amplitude decreases. When you compress it, the hopping increases. This spatial variation in hopping amplitudes is what creates the effective vector potential. As electrons hop around the deformed lattice, they accumulate a geometric phase that is exactly analogous to the Aharonov-Bohm phase an electron would pick up moving through a real magnetic field. From a mathematical perspective, this is all about Berry phases and Berry curvature. The deformation changes the electronic wave functions in a position-dependent way. The Berry connection is I times the expectation value of the block state U sub k with respect to the gradient in k space of its. The Berry curvature is the curl of the Berry connection in momentum space. Strain maps this momentum space curvature into a real space vector potential. Let me give you an analogy. Imagine you're walking on a flat surface versus walking on a curved surface, like a sphere. On the flat surface, parallel transport is trivial. On the curved surface, when you parallel transport a vector around a closed loop, it comes back rotated. This geometric phase from parallel transport on a curved surface is exactly analogous to what happens to electron wave functions in strained graphene. The strain creates an effective curvature in the space that electrons move through. Now let's talk about why this matters beyond just being a cool physics phenomenon. What can we do with pseudomagnetic fields? First, because the pseudomagnetic field has opposite signs in the two valleys, we can use strain to create valley filters. This is the basis of Valleytronics, where we use valley degree of freedom like we use spin in spintronics. Second, we can confine electrons using strain alone, without needing electric gates. The pseudomagnetic field creates effective quantum dots and waveguides through purely mechanical means. Third, we can study quantum Hall physics without needing expensive superconducting magnets. We can create Landau levels on demand using just mechanical deformation. Let me walk you through a more detailed calculation of the Landau-level spacing you'd observe in a strained graphene sample. The spacing between the 0th and 1st Landau levels is the Fermi velocity times the square root of 2 times E times h bar times b. The Fermi velocity is 1 million meters per second. Let's say our pseudomagnetic field is 100 Tesla. Plugging in 10 to the 6 meters per second times the square root of 2 times 1.6 times 10 to the negative 19 coulombs times 10 to the negative 34 joule seconds times 100 Tesla. This gives approximately 1.8 times 10 to the negative 20 joules, or about 0.11 electron volts. This is easily measurable with scanning tunneling spectroscopy. Here's another important question. If I apply both a real magnetic field and create a pseudomagnetic field through strain, what happens? Great question. In one valley, they add constructively. In the other valley, they subtract. This gives you valley-dependent Landau-level spectra, which is exactly what's observed experimentally. The total effective field at the K-valley equals the real field plus the pseudomagnetic field, but at the K-prime valley, it equals the real field minus the pseudomagnetic field. This difference is a direct signature of the valley-dependent nature of pseudofields. How do we actually create the right strain patterns in practice? There are several approaches. First, graphene nanobubbles form naturally when graphene is deposited on certain substrates. These create triaxial-like strain patterns automatically. Second, you can use an atomic force microscope tip to physically push on graphene and create controlled deformations with very specific strain profiles. Third, you can pattern the substrate with structures that force graphene to conform to a desired shape, creating predetermined strain distributions. Fourth, you can use materials with different thermal expansion coefficients and cool or heat the sample to induce strain through the mismatch. Before we conclude, I should mention that pseudomagnetic fields aren't unique to graphene. They can occur in any 2D material with Dirac or well points. Materials like molybdenum disulfide and tungsten diselenide can also exhibit pseudomagnetic field effects, though the coupling constants and optimal strain patterns differ from graphene. Surface states of topological insulators, which also have Dirac-like dispersion, can experience pseudomagnetic fields from surface deformation. Let me emphasize something crucial. The symmetry of the lattice determines what types of strain create pseudomagnetic fields. Uniform strain, where you stretch or compress the whole sample equally in all directions, creates zero pseudomagnetic field. You need broken symmetry. Shear strain, where different parts of the sample are strained differently, is what generates the field. It's all about gradients and non-uniformity. The pseudomagnetic field is proportional to gradients in the strain tensor. No gradient means no field. One fascinating consequence is that you can create quantum interference devices using strain alone. Imagine a strained region that acts like a magnetic field region. Electrons traveling on different sides of a strained region accumulate different geometric phases, just like in the Aharonov-Bohm effect. This creates interference patterns in conductance. Because the two valleys see opposite pseudomagnetic fields, the interference pattern itself is valley-dependent. This gives you a way to measure valley coherence and create valley-based quantum devices. Of course, there are practical challenges. Let's be honest about the limitations. First, graphene is strong, but not indestructible. Strains above about 25% typically cause rupture. So there's a practical limit to how strong your pseudomagnetic fields can be. Second, strain can relax over time, especially at room temperature. The configuration you create might not be stable indefinitely. Third, real samples have disorder and defects. These can scatter electrons and wash out the clean, Landau-level structure you'd expect from theory. Let me summarize the key differences between real magnetic fields and pseudomagnetic fields in a comparison. Real magnetic fields break time reversal symmetry and produce a Hall effect, while pseudomagnetic fields don't. Real fields are valley-independent, pseudofields are valley-dependent. Real fields max out around 100 Tesla in labs, but pseudofields can exceed 300 Tesla. And crucially, we have much better spatial control over pseudomagnetic fields through strain patterning. Looking forward, where is this field heading? There are several exciting directions. First, using strain to create and manipulate topological phases of matter. By designing specific strain patterns, we might create topological insulators or superconductors on demand. Second, practical Valleytronic devices, where information is encoded in the Valley degree of freedom, controlled entirely by strain patterns rather than magnetic fields. Third, using strained graphene as a quantum simulator for physics that normally requires ultra-high magnetic fields that we can't easily generate. Before I conclude, I want to emphasize the profound connection between geometry and electronic properties that this phenomenon reveals. In Einstein's general relativity, the geometry of spacetime affects the motion of particles. Mass curves spacetime, and particles follow geodesics in that curved space. Here, in strained graphene, the geometry of the lattice affects the quantum states of electrons. Strain curves the effective space that electrons live in, and they respond by forming Landau levels. This emergence of gauge fields from pure geometry is a beautiful example of the deep unity in physics. Electromagnetic forces, in a sense, are geometric in origin when viewed through this lens. Let me summarize the key points from this lecture. First, mechanical strain in graphene creates an effective vector potential that acts like a magnetic field on electrons. Second, these pseudomagnetic fields can reach strengths exceeding 300 Tesla, far beyond laboratory magnets. Third, unlike real magnetic fields, pseudomagnetic fields preserve time reversal symmetry because they're valley-dependent. Fourth, these effects have been directly observed using scanning tunneling microscopy in graphene nanobubbles. And fifth, this opens entirely new routes to creating quantum devices and studying high-field physics without actual magnets. Strain engineering of pseudomagnetic fields represents a beautiful marriage of mechanics, quantum mechanics, and geometry. It shows that sometimes the most powerful tools in physics come not from brute force, but from clever manipulation of symmetry and geometry. We can literally reshape the quantum reality experienced by electrons simply by bending and stretching a material. This is physics at its most elegant and powerful.